When you hear the word salt, you probably picture the white crystals on your dining table. But did you know that salt is far more than just a seasoning? Let's take a step into the lab. When hydrochloric acid reacts with sodium hydroxide, the result is something that's neither acidic nor basic. It's neutral. And what do we get? Sodium chloride, the very same salt we use in food. The reaction goes like this: HCl plus NaOH, NaCl plus H2O. Spelled out, hydrochloric acid plus sodium hydroxide produces sodium chloride and water. This is called a neutralization reaction. And common salt is just one of many kinds of salts formed through similar reactions. Salts aren't just random compounds, they're the offspring of acids and bases carrying the chemical DNA of their parents. Let's explore a few examples. Potassium sulfate, or KSO, is formed when potassium hydroxide reacts with sulfuric acid. Magnesium sulfate, MgSO, comes from magnesium hydroxide and sulfuric acid. Sodium nitrate, or NaNO, is born from sodium hydroxide and nitric acid. Ammonium chloride, NHCl, forms when ammonia reacts with hydrochloric acid. Now here's something interesting. Salts with the same positive or negative ion are part of the same salt family. For instance, NaCl and NaSO both contain sodium. They belong to the sodium salt family. NaCl and KCl share chloride. They're in the chloride salt family. Here's a common myth: all salts are neutral. But in reality, a salt's nature depends on who its parents were, the acid and base that formed it. Let's break it down. Strong acid plus strong base gives a neutral salt. Example: HCl plus NaOH, NaCl plus HO. Spelled out, hydrochloric acid plus sodium hydroxide gives sodium chloride and water. Strong acid plus weak base gives an acidic salt. Example: HCl plus NH, NHCl plus HO. Spelled out, hydrochloric acid plus ammonium hydroxide gives ammonium chloride and water. Weak acid plus strong base gives a basic salt. Example: CH2 plus NaOH, CHCONA plus HO. Spelled out, acetic acid, written as CH3COOH, plus sodium hydroxide gives sodium acetate, written as CH3COONA, and water. So how do you know if a salt is acidic, basic, or neutral? Use pH paper. pH around 7 is equal to neutral, pH less than 7 is equal to acidic, pH more than 7 is equal to basic. Every salt carries a clue in its chemical history, and pH helps us decode it. Let's zoom in on one of the most familiar salts, sodium chloride or NaCl. Yes, it's the salt on your dinner table. But in chemistry, common salt is a powerhouse, a starting point for several industrial chemicals. It's formed through a neutralization reaction. Hydrochloric acid plus sodium hydroxide gives sodium chloride and water. Reaction: HCl plus NaOH, NaCl plus H2O. Now here's where it gets interesting. In industries, salt water, also called brine, undergoes electrolysis to form three useful products: sodium hydroxide, NaOH, chlorine gas, Cl2, hydrogen gas, H2. This is called the chlor-alkali process. The reaction is 2NaCl plus 2H2O, 2NaOH plus Cl2 plus H2. Spelled out, 2 molecules of sodium chloride plus 2 molecules of water give 2 molecules of sodium hydroxide, chlorine gas, and hydrogen gas. And the story doesn't end there. The chlorine is used to make bleaching powder. KaOCl2 sodium is used to make baking soda. NaHCO3, and with a little chemistry, you also get washing soda. Na2CO3 10H2. So, from one salt, we unlock a chain of everyday essentials. Did you know that some salts aren't just dry powders? They actually hold water inside their crystal structure. This bound water is called water of crystallization, and it gives certain salts their distinct color and form. Take copper sulfate. Its formula is QSO4 for my 5H2O. It's bright blue because of those 5 water molecules locked inside the crystal. Heat it gently, and the water escapes. The salt turns white. It's now anhydrous copper sulfate. Add water again, and just like magic, the blue color returns. Another example is washing soda with the formula Na2CO3 10H2O. It contains 10 water molecules per formula unit. This water isn't just moisture, it's part of the salt's identity. Now let's explore a truly fascinating salt, plaster of Paris, or KSO4OS122H2O. It's made by heating gypsum, which is KSO4-2H2O, and gently driving out 1.5 molecules of water. The reaction goes like this. KSO4-2H2O. KSO4 was a 1:2H2O plus 1:2H2O, spelled out. Calcium sulfate dihydrate, written as CaSO4.2H2O, on heating, gives plaster of Paris, written as CaSO4.1/H2O and 1.5 molecules of water. That is, gypsum turns into plaster of Paris by losing water. But here's the cool part. When you add water back, it sets and hardens into gypsum again. This is what gives it the ability to form quick-setting molds and casts. Where do we use it? To immobilize broken reaction. KSO4-2H2O. KSO4-1,2H2O plus 1,1,2H2O bones. In making sculptures, toys, and ceiling designs. For smooth, quick-drying plaster work in architecture. Quick tip: always store plaster of Paris in airtight containers. It reacts even with moisture in the air. Let's quickly recap what we've uncovered about salts. Salts are formed through neutralization reactions between acids and bases. Their nature, acidic, basic, or neutral, depends on the strength of the reactants. Salts can be grouped into families based on their common ions. Everyday substances like baking soda, washing soda, and plaster of Paris, they're all salts. Some salts contain water of crystallization, giving them unique properties. Salts aren't just for taste. They are essential in industries, health, construction, and everyday life. So the next time you sprinkle salt on your food, apply toothpaste, or see a cast on a broken arm, remember, it's not just salt. It's chemistry in action.